Welcome back to the Dargslan networking curriculum. You've made it to Stage 3, Lesson 20. Today, we're tackling VLSM, or Variable Length Subnet Masking, the technique that lets you right-size every subnet instead of carving your network into wasteful equal chunks. By the end of this lesson, you'll be allocating addresses with surgical precision, giving each department exactly what it needs and nothing more. Here's the roadmap for the next few minutes. We'll start by looking at why fixed-length subnetting, the same mask everywhere, quietly burns through your address space. Then we'll introduce VLSM properly, and you'll learn the golden rule. Always design from the biggest subnet down to the smallest. Finally, we'll put it all to work on a real allocation problem, the kind you'll actually face on the job. Let's make the waste problem concrete. We've got a 24R, 192.168.1 points euro, and 4 departments needing 60, 25, 12, and just 2 hosts. The FLSM approach says, pick one mask, apply it everywhere. Split the 24 into 4 equal 26s, each holding 62 hosts. Marketing fits beautifully at 97% efficiency, but engineering wastes 37 addresses. Support wastes 50, and that tiny point-to-point link, it burns 60 addresses to carry just 2 hosts, 3% efficiency. Added up, we needed 99, allocated 248, and threw away 60% of our address space. It works, but barely, and at a steep cost. Now watch what happens when we right-size each subnet instead. Marketing still gets its 26 for 60 hosts. That one was already a good fit. But engineering drops to a 27, giving 30 addresses for 25 hosts. Support shrinks to a 28, and that point-to-point link gets a 30, exactly 4 addresses, 2 of them usable. Same 99 hosts, but now we've allocated just 108, wasted only 9, and we're sitting at 91% efficiency, with 148 addresses still free for future growth. But getting that efficiency requires following one golden rule. Always allocate your biggest subnets first. Here's why. If you start small, say a 30 at address 0, then try to fit a 26 right after, you're stuck. A 26 has to start on a multiple of 64, so you'd be forced to skip ahead to point 64, leaving those addresses from point 4 to point 63 stranded. Allocate biggest to smallest, and every block lands cleanly on its natural boundary. No gaps, no fragmentation. With that rule in mind, let's lock in a repeatable process you can run every single time. Step 1. List every subnet you need with its host count, including those tiny point-to-point links between routers. Step 2. Sort that list largest to smallest. Step 3. Pick the smallest mask that still fits each one. 60 hosts needs a 26, 25 fits in a 27, 12 in a 28, and a P2P link takes a 30. Step 4. Allocate starting from address 0, biggest first. And step 5, document everything. Network, broadcast, usable range, so you've got one source of truth to work from. Let's put that process to work. ACME Corp has handed us a 192.168 to 10, UOJ 24, and 5 groups to carve out of it. After listing requirements and sorting largest to smallest, engineering's 50 hosts jumps to the top and needs a 26 because a 27 only gives us 30 usable, which won't cut it. Sales lands on a 27. Support and guest Wi-Fi both take a 28, and the router-to-router link gets a 30. Notice how each mask is the tightest fit that still satisfies the host count. That's VLSM doing exactly what FLSM couldn't. Now we walk the block from the bottom up. Engineering claims the first 64 addresses, network at point 0, hosts from 1 to 62, broadcast at point 63. Sales picks up right after at 64 and runs through 95. Support takes 96 to 111. Guest Wi-Fi follows from 112 to 127, and the router link sits neatly in 128 to 131. And here's the payoff. We still have 124 addresses left over for future growth. That's VLSM earning its keep. Let's actually picture that allocation as a number line across the full 24. Engineering takes the first 64 slots, sales the next 32, then the smaller blocks for support, guest, and the point-to-point link squeeze in before the 128 mark, leaving that whole right half free. And notice the boundaries. Every subnet starts on a multiple of its own block size. A 26 has to begin on a multiple of 64, a 27 on a multiple of 32, a 28 on 16, a 30 on 4. That's the magic number rule. Break it and the subnet simply isn't valid. Speaking of breaking rules, let's talk about the pitfalls that catch people out. The biggest one is allocating your smallest subnet first. Drop a 30 at point 0, and you've just blocked every future 26 from starting there. Always sort biggest to smallest. Watch for overlap, where a 26 covering 0.0 to 63 makes a 28 at 32 illegal. Leave growth room. Don't forget point-to-point links between routers, and stop thinking in old-class boundaries. Size to actual need every time. Now that you know the pitfalls, here are 4 heuristics that seasoned engineers actually use in production. First, double today's count. If you need 25 hosts, jump to a 27 or even a 26 because growth is inevitable. Second, leave gaps between allocations so a new department slots in without a re-IP nightmare. Third, standardize on common sizes like 24, 26, 28. Predictability beats cleverness. And fourth, reserve the low addresses of each subnet for infrastructure. 0.1 for the gateway. Single digits for network gear, 10 and up for users. Scriptable, memorable, and your future self will thank you. Let's lock in the 5 ideas that should stay with you long after this lesson ends. Fixed size subnetting feels tidy, but it quietly burns addresses every time a small group gets a full block. VLSM fixes that by right-sizing each subnet to its actual host count. Always start with the largest requirement and work down because the small ones slot neatly into the gaps. Pick the smallest mask that covers your needs, then step up once for growth. And never forget the magic number rule. Every network address has to land on a clean multiple, no exceptions. And here's your 1-page cheat sheet, the whole lesson distilled into something you can screenshot and keep beside you. FLSM versus VLSM at the top, the 5-step design flow in the middle, and the 2 rules that catch most beginners, overlap and growth, anchoring the bottom. If you ever get stuck halfway through an allocation on something like our 192.1168.1.0 24 scenario, come back to this slide and walk the steps in order. It works every time. That wraps up VLSM, but the story isn't over. In the next lesson, we flip the script entirely. Instead of carving one network into smaller pieces, we'll combine multiple networks into one. That's SID and supernetting, and it's how the internet itself keeps routing tables manageable. Catch you in lesson 21. And if this helped, you know where to find more at dargslan.com.